Hi, welcome to the next of our series of mini lectures. Today's going to be a little bit unusual in that we're going to cover material you've already seen, probably in modern physics, maybe in semiconductor devices, even back in high school. But it's very important you have a good conceptual grasp of this material before we move on. Otherwise, a lot of the diagrams are not really going to make sense to you. So we start off here with a picture of the Bohr atom. And Niels Bohr was the guy who came up with this model of the atom that looks a lot like a solar system, and you're familiar with this. In the center of this atom, there's a nucleus, and surrounding the nucleus are orbitals of electrons. In the first orbital, labeled 1 here, you can count 2 electrons. In the second orbital, you have a possibility of 8 electrons, 2 s electrons, and 6 p electrons, for a total of 8. It turns out there are, I think, 18 in the third orbital and 30-odd in the fourth orbital, and so on and so forth. And we're familiar with this, although in this picture of the atom, there's a lot of concepts that aren't described very well. Things aren't really like this. An atom's not really like a little solar system being orbited by little tiny balls that have charge that we call electrons. And I want to explain this picture of the atom so we understand what's going on and can understand some of the diagrams that we use in photonics. And many of these are like schematic diagrams in engineering. They tell something very specific, but until you understand what the notation means, they don't make a lot of sense. And we don't like to draw all these circles with a little nucleus at the center of the atom. That's a very inconvenient way to do it. So the way we represent the Bohr atom is with a diagram that looks like this. We take the allowed energy levels, and remember, electrons can only be in particular energy levels. They can't have energies or orbitals that aren't part of the model. And we do it like this. And this allows us actually, although it's not done in this picture, to put numbers on each of these different energy levels. And we can say the difference between energy level E2 and E3 is this by reading off the graph. Now in lasers, we're working with optical frequencies. And it turns out that while you can take an electron off of an inner orbital, say here, and move it out, it requires an immense amount of energy to do that compared with the energy available in the visible photon. So the only electrons that we're going to be working with are the ones in the outermost populated orbital. Notice we've got electrons in orbital 2 but not orbital 3. And so what we do in this case in optics is we talk about the lowest energy level, the one at effectively 0 energy, as being the lowest orbital that in the ground state, or at the minimum energy of the atom, in fact has electrons in it. It's not, but that's how we deal with it in optics. And a physicist who does X-rays or gamma rays or neutron scattering would certainly not use this model. But with this, we see that then the electrons in orbital 3 go into state 1 here. And this notation, I admit, is a little bit confusing, but it's important to know exactly what we do when we draw one of these pictures right here, because we're going to be using this over and over and over again in this course. So on and so forth. We just populate these energy levels, starting with the lowest populated energy level. Now, you all are probably aware that an electron is not like a little ball of charge. It doesn't behave like a billiard ball or a BB or a grain of sand. An electron has wave-like properties, and that means in order to describe the position or momentum or velocity or energy or anything else about an electron, whether it be an electron in free space or whether it be an electron that's bound to an atom like this, we need to solve a wave-type equation. And in electromagnetics, of course, we use Maxwell's equations. You're all very familiar with the complexity that arises out of that set of equations. In quantum mechanics, the study of the mechanics of how things behave on a scale that's very, very small, in the order of 10 to the minus 9, 10 to the minus 10 meters. On this scale, electrons have wave-like properties, and the equation is called the Schrodinger Equation. And if you take a quantum mechanics course, you'll learn about the Schrodinger Equation, but our purpose here is not to derive the Schrodinger Equation and the orbitals of a simple atom, because that's a lot of math and doesn't really give us any insight into our class, which is understanding a laser. But let's go ahead and take a look at this in a little bit more detail and what wave-like properties, or treating an electron, a mass, like it's an electromagnetic field really means, because there are some things that fall out of that are a little bit and so, as I said, we're learning quantum mechanics, and you can read this as I talk, but as I said before, all matter has wave-like properties at the scale of 10 to the minus 9, 10 to the minus 10 meters. We solve Schrodinger's equation, and like Maxwell's equations giving an electric field that has a complex amplitude, remember it has a cosine and I sine theta component if you have a wave-like property, because there is a complex part to that. It turns out the motion of the electron is governed by a complex wave equation. But what Schrodinger's equation calculates isn't an electric field or magnetic field like Maxwell's equation. It gives us a complex probability amplitude of finding an electron anywhere in space. So an electron isn't someplace. It simply has a complex wave-like nature that has an amplitude for finding it anywhere in space. Now, this is pretty confusing. And you have to make the analogy between the complex probability amplitude and a sinusoidal electromagnetic wave, which you're much more familiar with. If you want to find the energy of a wave, you basically multiply the field by its complex conjugate, or take the magnitude squared of the electric field, and the actual probability, the real probability of finding an electron at any one point in time, is equal to the square of the absolute value of the complex probability amplitude, just like comparing power and electric fields or power and magnetic fields. The probability is not a complex value because we take the magnitude and square it. It's a real number. But again, it says that it doesn't say you're going to find the electron in some place. It'll just calculate where the electron has a good probability of being. And this symbol psi is essentially the equation for the electron. It's the wave equation of the electron, and this is going to tell us what this probability amplitude is. So psi, and let's write this, is this probability amplitude that we've been talking about. And if there are two possible wave functions, two possible states, that's just two orbitals an electron can be in, two possible ways to put that electron, if you will, the overall wave function is simply the sum of the two wave functions, and the probability then to find the electron, where capital P is a real probability, is simply the modulus squared of those two complex equations. And this is actually kind of interesting, and this is where things get a little bit different than your everyday experience, and you're sort of going along and nodding and think you understand this. But let me explain a little bit more. If you take a macroscopic object, something like a penny or a nickel you would have in the everyday world, and you flip it up in the air and you ignore the possibility that it might land on its side, then there are two possible alternatives, two states for that nickel or penny to be in, heads or tails, depending on which way it lands. When it's in the air, you don't know which it is. The probabilities haven't sort of come into being yet, but after it lands, it's either a head or a tail. However, the probability in quantum mechanics, since these are complex numbers, remember, is essentially the probability of state 1 plus the probability of state 2 plus a probability that can be the superposition of state 1 and then a superposition the other way where the star is a complex conjugate. And essentially what it means is if you have an electron that is possibly in two states, it can be in state 1, it can be in state 2, it can be in state 1 and 2, or it can be in state 2 and 1. And so just like you have with waves, electrons have superposition. They can have interference, constructive interference or destructive interference. They can be a sum of many different waves, just like you could superpose electromagnetic waves. And the point of all of this is the law of computing probabilities for electrons is not that of classical physics. And we need to understand that. So let's go ahead and talk about this a little bit more as how it applies to lasers.